Welcome everyone to today's webinar, Cell Profiling and Biomarker Discovery in a Spatial Context, a guide through the analysis of your spatial biology data. I am Thelma Santos and I will be the presenter today. Hopefully, last week you were here to hear Amy talk about our predefined antibody panels, and the week before you heard Sarah and Jenya talk about the MACSima Imaging Platform, which is the whole solution for spatial biology, the only one. Next week, we will have the pleasure to have our user telling you your real life story with which you use our system, the talented Dr. Kvede Heite, and please be tuned, it's very important. But today, I will focus on one aspect that often is not really talked about that much, which is the analysis of your data, what gives meaning to your data. And I will showcase you our software, the MaxIQ View. Now, just to put in perspective, previously, first webinar, Sarah and Jenya presented you the whole MACSima Imaging Platform. It's very important for us to tell you and to show you that we cover you from A to Z, not only with an instrument, with the full package here, instruments, sample carriers, antibodies and reagents, even predefined panels like last week was presented, and our software. And last week, Amy really took time to explain to you what wonderful product is our antibody panel predefined, specifically tailored for TME research. But now I'll be showcasing the software and how it works. For that, I did a recording with the screen and my voice because there's no way we can show you what all that we can do with slides. There's no way. So please enjoy. Okay, so let's jump right in. So to give continuity to the series, I'm going to show you here some analysis I made using the colon sample that Amy already showed you, and of course run with the ReaScreen IO panel that she also presented to you. Disclaimer, I will not do the analysis live here because there is just not enough time, but I did a nice analysis before and I will walk you through it, some of the nice features we have. There is no time to go through all the features, unfortunately. If you feel interested after this or even just now, feel free to contact us. We will gladly explain you more what the software can do for you, and we have a big amount of people that are actually very nice and proficient with the software and are happy to support you in everything. So let's just go to it. So here you can see the software, and I'm showing it live because there's no presentation that could show it better in another form. So you can really have a feeling from it, and then you don't feel cheated because I'm going to do this in one go. So the first thing you see is that right now I'm showing you some markers highlighted, and you can see them because there's a eyeball. I could also show to display each marker, as you can see here. And the interesting thing is as you navigate through it, you can see the gray value in each pixel of this. I will hide it just to not have this too crowded. Also, I will show this in one screen, and it's not normally how I work with the software. So excuse the crowded area because normally I go through different screens for that. So the first step that you have to do before you even start your analysis is check your images. So we can turn on and off markers, as you can see here, and choose the colors in which we want to display them. The easiest way, though, is to select only visible and just go through it and navigate through it, clicking through all the images and identify if the markers are okay or not. This is just a visual representation. And of course, you always have access to the histogram where you can rearrange the images for your eyes. But of course, the gray values are not changed. When it comes to checking if your markers are okay, of course, you can just inspect visually, but numbers are always more important, so that's why you need the histogram. But we also have a very nice tool here, our line profile, I will show you, where you have the ability to trace a line and see really the values of background and the markers. And not only you can do this for each marker individually, but you can also select all the ones displayed and you can see the color. So you can really see proportionally what are the high and the lows and how high, how low. And you can do this in a way also where you can select several ones like this, and then you can really navigate through the different markers that you want to see. And of course, all of this can be extracted as CSV file if you want to use the number for something else. And you can also use the smoothing or a more rough way to quantify everything that you see there. Another very nice inspection that can be done at the pixel level that we have is a correlation matrix. Now it's calculating, and it calculates when you open it and as you extract it. When it will appear, I will show. Let me just in a little bit so it goes faster. But what this is a correlation. It will give you an x between two curves. Highlighted will be close to big as it's closer to blue. It's positive to which is later. There's no, then you will have something like a dot that will be 0. And when you select it, you see the two markers directly, and you see also here the number. So you see close to 0, you barely see anything. A big number is, for example, here, a higher level of correlation, and you can navigate through it. It's interactive, and you can also extract here the information, which is always helpful. Now, going back to the data set, once you are inspected and you judge that your data set is good enough to follow the path of analysis, the first step of every analysis will always be your segmentation. And I already run the segmentation just for time's constraint to show you everything. So here you can see the mask of the segmentation, where you can see my nuclei and my cytoplasmic markers. And when it comes to the segmentations, what we offer is a very the mainly used algorithms for nuclear segmentation, which is based on the watershed. Here we use by default the TAPI, but you can actually choose any of your markers. If you have a better marker for the nucleus, you can choose another one and a set of easy to use parameters. The cytoplasm is done as a secondary step. You first identify nucleus, then a cytoplasm. And for that, we have different methods. We have what we call the donut. Some people call it differently. It's just an expansion of your nucleus boundaries with a defined width. Or you have the constrained donut, where you can change range, vast range, or all the markers like this. And what happens with it is that it will follow the shape of the markers, and you will have this irregular shape for a better understanding of your segmentation. If the segmentation is not still how you want it, or because you already define a very good method in your lab, you can always import your mask image and then follow the rest of the quantification. If you do not have nucleated cells or have a very complex sample where nuclei can be lost or cells have a very, very complex shape, you can also do image-based analysis, where we could call superpixel. And if instead of the unit of your analysis be the cell, it will be a little square. We are looking into increasing the algorithms that we provide. And of course, any feedback and knowledge is always welcome. We want to go into that direction, but having such a nice tool already, we wanted the customers to already start using the software and really for their benefits. This is a software made for biologists. As you can see, it's a lot of interactivity and visual feedback, and that is made specially because these complex kinds of data sets can be overwhelming to navigate through, and the hypothesis of your observations can also be difficult to really follow or have an idea. So that's why this is made in that manner. So once you have your segmentation made, like, the sky is your limit, and you can go at different directions when it comes from analysis. So here I'm going to show you what we call our workflow editor. It seems very complex like this, but it is actually there to help you navigate through your analysis. And how is it? So the way you can see is that you clearly do a connection between your objects and your group of objects and how you work with them, and you see how they all are connected. And not only are they connected for you to understand how they are connected, but if you change the connection, everything is updated automatically. So if I decided that I do not want this group of cells be the basis of the rest of my phenotyping, I could just connect another one and it will recalculate. For the sake of time, I will just not do it right now because it would have to recalculate, but this is how it works. Now, as you can see, there is different ways, and as I said before, there is different ways where you can go at for your analysis. So here I will touch point in some aspects of it. There's probably a lot of other things you can do. The tools are there. And if you want a demo and try to play with it, please reach out again. We will be happy to have your feedback on it. But here I'll do the most common ones. So the first step I did was what I call a biased kind of phenotyping. So it's based on my knowledge. It's selecting or defining cell groups based on what is known. So the first step I did was tissue phenotyping, or sometimes called tissue phenotyping, and I did it with markers. So I did a scatter plot that you can see here, where I could really see a way to separate in 4 different groups the cells that I've seen in my data set. So the colon carcinoma here has CD326, so EpCAM, as a marker normally for cancer, but we know that there's also healthy EpCAM there. So we can see that you could, if you zoom in, see a clear difference between the normal EpCAM and the not normal EpCAM. And then I use the HLA to really define immune cells versus non-immune cells, and also separates the cancer. So I did it in a quadrant method. Now I would turn on, and the thing that you can see directly is that you see the colors in the image and in the plot. So let me just move it a little bit. And the way I did the quadrant is that I defined where it's supposed to break. So I can change it a little bit, of course, here, because there's a lot of cells. You can see that it takes a little while to recalculate. And of course, if you remember in the workflow editor, we have a lot that is connected to it. So everything now is being recalculated and all the numbers. And something that I just forget to mention, of course, when you do your segmentation, you'll have your total number of cells, and every cell you select or gate, you also have the number of cells that you gate. So you have a real number. You can really quantitatively measure the amount of cells in certain groups. So the way I did it is, and as you can see here, you can read the legend, is that I separate the cells between the immune cells, the normal epithelium, the tumor cells, and the rest of the stroma. And that was the first thing that I separated. And after that, what I did was to do a phenotyping of known immune cell types, so NK cells, neutrophils, and I made this merge to make sure that I would not select the same cell in 2 groups differently. So this takes a little bit of use to it, but then I could identify all these kind of cells that you can have here. So now in the group of immune cells, the ones that you see in green. Now I will turn this off, and we will see, and I will put this in the DAPI because then it's easier to navigate through, and I will delete this. And it's easier to navigate and see the cells pop up. Now I can see where my Treg cells are, my mast cells, my neutrophils, my M1 and M2 macrophages. So I first selected macrophages and then divided between M1 and M2, monocytes, NK cells, plasma cells, B cells, helper T cells, and cytotoxic T cells. So now you have here the legend, and you can see the areas where our immune cells are, and you can see some hot spots, and you can see that here it's quite heavy and all around this area here, and you see here it's less dense, but you have also a big number of immune cell types, so you can see them already like this. And now, even if I go to this to my graph here about the immune cell types, you can see that the cells are colored only here because that's the immune cells, and you can see more or less how they are here. And all of this is transported throughout the software, this kind of interactivity. I mentioned this biased kind of phenotyping. There's also another method that is very frequently used, which is the dimension reduction. We have the option to do t-SNEs and UMAPs, and we have some clustering methods. that you can do when you do a UMAP here that I run already. So you can see the UMAP here, and you can see the different color-coded cell types that I did. And what I can also now select is the the tissue phenotyping that I did before. And here you can see the clear separation between the cancer cells and the normal epithelium. And then here the immune cells, and here the rest of the stroma, for example. And another advantage of this software is that you have this interactivity throughout. You can also treat this UMAP like any scatter plot, and if you decide that you want the visual clustering here that you have on the UMAP to be the source of you defining groups of interest that you want to compare, then you can also do it like this on the map itself. And one thing that we end up doing throughout this kind of analysis is comparing cell types, right? So now what I can do is just see from these cell types what kind of markers they have. So maybe I can identify the kind of markers they are. So if I go here to the workflow editor, and now you see that I have my UMAP, the gates I created, I can do a heat map and check for the features, for the expression features, for example, and I can have them represented here. So you can see that one group is very small compared to the other two. So what I like to do is averaging. Normally this helps just navigate a bit easier through the different markers. So here you can see the expression profile, expression signature panel, if you want, the different groups that are defined in the UMAP. And all of this can be refined as you wish. This is replicated throughout the whole software. You can do heat maps, or if you want one specific kind of pattern, you can also do a strip and violin, and here just focus on the expression markers as well. And here you can see how they are through that one group of cells. At the end of the day, that's what you do. You compare group of the cells, and the way you want to compare them can be via phenotyping of known cells, or it can be via some more blinded clustering or organization types. We also have an option to normalize the data, as it's here shown here. And that's more or less how it is when it comes to identifying cell types. So you can see the software is really here to help guide you through this vast amount of opportunities that you have when you run such a kind of data set. Now, I don't have much time, and this is a little bit fast because of the lack of time, and I really want to show how amazing this software is. But it's always a bit difficult to condense everything, especially in 20 minutes. One part that is quite interesting with these new technologies is the spatial aspect of it. And I just quickly want to mention our distances and density metrics that we have here available. So of course, the information about the X, Y coordinates of the cells that you can find here on the table, you have access to all the raw data. All of this can be exported, and you can navigate through it. You see there is a lot about the markers themselves. There is also a lot about the cells, and you have, of course, the XY coordinates of the cells. But it's very overwhelming, and just looking at it, you cannot really have an idea. So having a visual representation of the distances is something of interest. So what I did here, that you can see on the workflow, is that I did a relative distance to the tumor. So let's just see. So here we have the tumor, and here is the distance map of the tumor. So you can see what it looks like. And what does that allows me to do is that it allows me to create such a graph, and then I can gate on this graph. Let's turn it on like this. And now you can see the cells here represented as the tumor, the cells closer to the tumor, a bit further away, and then the ones very much further away. And this can help you identify several things about your sample. You can run a heat map between these different distances, and now you can see that the difference of markers between the tumor itself and the ones that are really close to the tumor and then a bit more far away. You can have an idea if the tumor is being constrained or not by immune cells. You can have an idea if the prognostic will be bad because it's very invasive because of the markers of the cells who are close to it. You can identify a little bit also the signature of the cancer itself. So this can be ways to look at it. The other one that I mentioned in terms of spatial was the density metrics. And this time, instead of focusing the density on the tumor, I did the density on the immune cells. And what does that look like? So let's now turn off here. So you have my immune cells that I selected here. And what I did is that I ran a density map, and the density map looks like this. So you can see the areas where the immune cells are more dense, and this can help you a bit figure it out what is happening there, and also what kind of cells are in these areas besides immune cells or itself the immune cell. So one example I have here is that I can show a box plot where I selected my group of immune phenotypes, and now I see the ones that have higher values are in higher dense population, such as the B cells. And for example, the mast cell seems to be a bit more splayed throughout the sample. So now if I look at my B cells, here, you will see that the B cells, they turn red. It's a bit unfortunate because it's also red here, but they turn red in the denser areas as it was shown. And the mast cells, for example, they are here, they're in this purple, and they are a bit more splayed. They are not so much in these areas. So this is an information you can have about, it's another level of information about not only the immune phenotypes in your sample, but also how they are organized in your sample. And maybe you can find a way to correlate this with a good or bad prognostic or any other way to describe your sample. And now there is always much more we could talk. I could talk about this for hours, but I hope that you could now enjoy a lot of the tools that we have. At the end of the day, you select cells based on the features that we have measured, and after that, what you do is that you compare them and you try to identify markers of interest in subpopulation, etc., to make up your mind in a possible explanation of why that is. Now, you've seen that this is a quite complex data workflow that took some time to do. And now you think, oh my God, if I have to repeat that and you only show me one data set. So now I wanted just to take the time to show you that what I did was that I apply the same workflow to another data set, the PDAC data set. Now you can see that I'm back in the same place. I didn't want to show just a different one. So this is where we were with our analysis. Now I'll jump back to the PDAC where I apply the exact same workflow. So if we zoom out, you can see here you have the same. I have my immune profiling, you have my tissue phenotyping, distance to tumor, immune density as well. And now you can see how it looks like in a different sample, which is this PDAC sample, but with also the screen panel. You can see in this case that clearly the immune cells are differently organized here. They're clearly more here. Also, they are close to what we would consider, I consider the normal epithelium, as opposed to the cancer areas that we can see here. You can see the distance maps. Let's do it like it was before. So let's turn off this so you can see a bit better. So you can see the distance map. So if you compare it with the tumor, it works in a similar way. So you have the tumor, the distance map. You also have the immune cell density, where here it's in yellow, but I had it as a gradient before. So I think it was either the spectrum, exactly. So you see clearly where the front of the immune cells are. In here, we can do a similar part where the feature here could be the immune density. And in that case, I would choose my immune phenotypes. And in here, you see that it's a bit different from before, where the B cells are still more in human spaces, but now it's not as it was before. And the mast cell are again the more splayed. That's an interesting part, although it's a bit different, but you see that the shape of the graph is quite different here. And again, so now you can have not only the exact same workflow where you see the same gates and everything, you can alter these gates back to it. It's all interactive. You can adjust it, or you can simply extract the number of cells exactly in all of your groups and compare one to another. So the total amount of cells here on the segmentation is different. It's about almost 60,000. And then here you can see the exact number and then make the proportions of this group of cells. You can compare the group of cells and then extract everything that you have done in a very easy and fast and convenient way. And I know I seem biased, but I really think that what we have here is very special. And I hope that it could convince you, give you some interest in it. And again, just contact us for any questions you might have. And now let's jump back to my presentation. So I hope you really enjoyed this little demo. It could take hours, it could go on forever, but this was just to really show you the power of MaxIQ and really to reiterate how much we want and wish to cover you and help you in your spatial bio adventure from A to Z. So that's why we explained to you this in the first webinar. That's why we also are bringing to you these new panels for research. That's why we are working so hard in making our software better and better. And also to reiterate that we cover you from A to Z because it's only complete when you really finish analyzing your data. I'm going to go fast now because I want to really have time to answer some questions. Thank you for your attention, and I'm happy now to take any question you might have. Always here to try to support you. And I would like to just let you hear with the title and the presenter of our next webinar, Dr. Kveda Heide. It's very talented, really highly recommended. This is the time to really see a real story in action with our platform. Thank you.